The goal today is to learn about the so-called Monjang verification. Okay. So after Brennan's theorem, so one may wonder what kind of these properties is the Brennan's solution given by this convex function has. So Monjang verification is the answer, and we see what it is and then some applications. Okay, Brennan's theorem. So for this distance square course in the Euclidean space, when the source measure is absolutely continuous, we know that the optimal transport plan is unique. Okay? And not only that, it is given by a measurable mapping because of this marginal condition for pi bar, it should transport the source measure mu to the target measure mu. But not only that, the mapping is given by the gradient over convex function. Okay, and here the convex function may not in general be differentiable, but at least for this bounded, in particular the bounded target domain, we see that gradient, sorry, the function nu is Lipschitz, so it is differentiable almost everywhere, and with this absolute continuity of mu, and differential almost where with respect to Lebesgue implies differential almost everywhere with respect to this mu measure. Okay, so that's why we can write this. Okay. Yeah, so that's it. So this is called Monge solution. Okay, then now from this, we can derive the so-called Monge equation. Okay, so here let's start with defining Hessian. So given a function, let's say it's twice differentiable, then the Hessian of the function is a matrix. It's a symmetric matrix. Okay, so each ij entry is given by this ij second derivative of the function. Okay, this Hessian matrix. So you will see this Hessian matrix very often in the literature, of course in PDE, but in other contexts as well. Okay. So now what is the equation? So you consider the Hessian of a function u. So here, this u is a convex function. So if u is convex function, let's say u is twice differentiable, then Hessian of u, which is the matrix with the second derivative. So if the function is convex, we know that the second derivative is one variable function, then convexity means the second derivative is non-negative, right? So likewise, for the multidimensional function, convexity implies that this Hessian matrix as a matrix is non-negative. So as a matrix, okay? What do I mean that a matrix is non-negative? What does it mean? Yeah, it's positive set or non-negative semi-definite. And what does it mean? Yeah, so that's one can understand it that way. So let me just write it down. So this is symmetric, asymmetric matrix is non-negative, is by definition, if all its eigenvalues are non-negative. Okay, so that's, so here, okay, this non-negative matrix, and then of course you can take the determinant of this. So this quantity is non-negative. But anyways, the point is that this G is at gradient Ux. This G is a density of the target measure. G is the density of the target measure. And then F is the density of the source. Okay. So the claim is this Monge amplification is equivalent to this transport property that gradient nu as a mapping transport the measure mu to nu. Okay, so this, I mean, if this holds for u, then it implies this. On the other hand, if u is twice differentiable and u satisfies this transport property, then that implies this Monge amplification. Okay, so let us just explain why this is related to this Monge amplification. That is just basically calculus, but let's do it together. Okay. So from this condition, this transport condition can be written in the following way. So for any continuous function, okay, this measure mu integrating the function let's say psi evaluate at gradient ux is the same as the function at y integral of the function c at y so c evaluated against this measure nu. So you can derive that these two are equivalent. Okay. Okay, I'm not going to explain it. So if you have any doubts, and that is your exercise. Okay. Okay. Then after that, or you can just take this as your like a definition of this property. Okay. Then from this gradient u, you can take this change of variable that this equal to y on this side. Then sorry, the other way around. So this y, you view it as gradient u at x. Then you replace these y's with gradient u x. Okay, it's just change of variable. All right. But then this change of variable of dy, which is d of gradient u x. So now this is a measure with respect to the x variable. Then what should be the density? So that density is what you learned in multivariable calculus. That's nothing but the Jacobian determinant. Okay, so you have this mapping gradient nu. This is a mapping. So if this is t, then dtx is the same as the Jacobian gradient of Jacobian determinant of t times dx. Okay, so you can put that Jacobian determinant there. Okay. Okay, then you have, so this is Jacobian determinant. So you have this left-hand side is equal to this. We have this because just we replace y with gradient u, change of variable. And then you have this g gradient ux, and then determinant of, so here we differentiate the gradient of u. So derivative of gradient u is nothing but the Hessian. Okay, it's the second derivative. So that's why this Jacobian determinant of gradient u is nothing but determinant of Hessian of u. Okay, so this expression is here. Okay, and then on the left you have this expression, and this c is common, but this holds for any c. That means this quantity and this quantity has to be the same. So that's why we get this. That is exactly the Monge amplification. Yeah. Question. So at the moment, we are assuming that u is twice differentiable. Then this should hold at every point. So assuming. Okay, other question? Okay, so we get this nice equation. So Mongian equation is not only in optimal transport. I mean, if you consider some geometric problems, you will see some equations involving determinant of Hessian of some function. Okay, so this is very common in geometric context. Okay, and this determinant of Hessian correspond to, I think, to scalar curvature of some space. I mean, that is something like that. Okay. So you can also see such similar equations a lot in convex geometry. Okay. Then really, the determinant of Hessian of U is related to the curvature of the graph of a convex function. Okay. All right. Okay, then an important exercise I really want you to do is the following. So this Mongian equation holds for the Brenier solution. For the Brenier solution, meaning you have gradient of U pushing forward a source measure mu to the target measure mu. Okay, but we have other cases with other cost functions, right? Brenier solution is for the distance squared cost function, but there are, of course, other cost functions one may want to consider. So, and that's the context of Gangbo-Mechan's theorem. Then you have also Brenier type solution there in Gangbo-Mechan's theorem, right? And then you have some kind of mapping coming from Gangbo-Mechan's theorem, transporting your measure mu to the target measure mu. Then you will have some similar relations like this. So you will have some equation similar to this, right? Am I making sense? So I want you to derive such an equation, okay? So in the context of Gangbo-Mechan theorem, derive a PD for your Brenier type solution, okay? That should be a very nice exercise for you. Question? Okay. Okay, but one thing I should say is that not every Brenier solution is differentiable. So the function nu, the potential function nu in Brenier solution, okay, sometimes it is differentiable, but very often, depending on your source measure mu and target measure mu, they are not differentiable in general, okay? But still, the point is that this Mongian equation can still be considered in a much more general context where your function u is not necessarily twice differentiable, okay? Okay, that's the context of the next slide. So our function u, the function u, okay, uh, is convex. Okay, and another thing is that with especially the source and target domain compact, then u is ellipsis. Okay, gradient u is bounded. So that function u is at least differentiable in the first order, almost every sense. Okay, but now to consider the Monge amplification, you need second derivative. So first derivative is not enough to write down the Monge amplification. So you need some kind of second order differentiability for the function u. Okay, so then Alexandrov answered that question. So Alexandrov has this theorem in the context of convex geometry. Okay? Not in the context of optimal transfer, but still, I mean, fortunately, we have this theorem developed by Alexandrov saying the following. Consider a convex function. Of course, semi-convex function is nothing but convex function plus smooth function. So in terms of differentiability, semi-convex function and convex function are the same. Okay. So suppose your function is ellipsis and semi-convex, in particular convex. Then Alexandrov says for almost every x, the second derivative exists. Okay. And more precisely, it means the following. For almost every x, you can write down this equation, okay? For any h, a vector in ID, you just add this h to your original location x. Then you compare the difference between the function phi at x and the function phi at x plus h. Then their difference is given by this first order approximation plus this second order approximation. This is second order approximation because you have 2h. And then the error term. Okay. Once you can write down this equation, it means this A is the Hessian of phi. Okay, at that point x. Okay. So you can just consider Alexandrov's theorem just providing second order differentiability of a convex function in for almost every point. Okay, so that's what this is. And for convex function, the convexity of the function, I mean, you know what it is, right? So convex function means its epigraph is a convex set. So convex function means in ID, a convex function, that means its epigraph. The set above its graph is a convex set. That's a convex function. Okay? But when the function is convex, then, and if this second derivative exists at a point, then that Hessian as a matrix is non-negative. That's what you can verify. Okay. Exercise. Okay. Question? So for ellipsis functions, we have this almost everywhere differentiability, Gaudian theorem. For semi-convex functions, ellipsis and semi-convex functions, so semi-convex function has like a better property than ellipsis function, right? Because it is related to the second order property, second order differentiability. So there, Alexandrov theorem says, indeed, the convex functions or semi-convex functions have this almost everywhere second order differentiability. Okay.
I have a quick question.
Yes.
So intuitively, you'd think that this is the best regularity we're going to get from the convexity. Is that the case?
So best generic regularity. Generically, I mean, any convex function has this property. But of course, there are better convex functions that are actually C2 and even smooth, right? Maybe, did I understand your question well?
Yeah, basically. Yeah, thank you.
Yeah, so the point is that this is generalized theorem, okay? Basically, for any convex function, okay, this ellipsis, but basically for any convex function, you can write down this for almost every x.
Sorry, I thought that if it's convex, it's already Lipschitz almost everywhere. Is that, or it's locally
Not
Lipschitz?
necessarily. I mean, the
Locally
convex
Lipschitz.
functions can be like this. Yeah, so phi positive infinity and 0 x in C is C convex. Yeah, so see, if you have convex set, then you give 0 at convex set and then elsewhere infinity, then that function is convex. Else in this definition, this epigraph is a convex set, right? But this is not ellipsis.
Okay, yeah, thank you. I was thinking of locally Lipschitz on the interior of the domain.
So, yeah, local ellipsis. Yeah, so right. So yeah, convex function. Besides this having infinity, convex functions are local ellipsis. I mean, only this kind of cases are where this local ellipsis is violated. The convex function is non-continuous only when you have this kind of property. Because convex function, if you remember, convex functions have the supporting hyperplanes, okay? As long as the supporting hyperplanes have bounded slope, that means there is a local ellipsis. So the only way to not to have a continuity or a local ellipsis is to have an unbounded slope for a supporting hyperplane, which is this case. Okay, am I making sense?
Yes, thank you.
Okay. Good question. Convex functions are not necessarily ellipses. Okay. So that means now we have almost every second differentiability. So that means for convex functions, at least we can make sense of this Mongian equation at almost every x. Right? Because at almost every x, you can write down the Hessian. So at least the equation can be written for almost every x. And in fact, the Brenier solution, so here to derive this property, we assume that U is C2, but you can just assume U is convex and ellipsis. Then you can write all these. So when U is just ellipsis and convex, of course, this definition, this expression for this equivalent expression for this transport property, it holds for any measurable mapping. Okay, you don't even need like, I don't know, gradient u. It's just, this holds for any measurable mapping T. Okay, and then you can do this change of variable for any measurable mapping T. Then the only question is what happens to here. Okay, there for convex function, the gradient of convex function, I mean, almost every gradient of convex function, you can still write down the Jacobian determinant and get this. That is the conclusion here, that you can still write down this Monk generalization, but now for almost every x. Okay. So in conclusion, in the context of linear theorem, in particular where the source measure has this density, okay, you can write down the Monk amplification for the Brenier solution U, the potential function U. And this equation is satisfied almost every time. Question?
I have a quick question.
Yes.
Just about this PDE, can we classify this PDE in terms of, elliptic, hyperbolic?
Oh, great question. So this type of PDE is called fully nonlinear PDE. Why fully nonlinear? Here the nonlinearity is like, this is Hessian, but the Laplace equation is the same as taking trace of this thingy, right? So here Laplace equation is just here the sum of eigenvalues. Okay. And then determinant of Hessian view is product of these eigenvalues. So here there are something in between. So you can actually compute identity plus t times Hessian of u. Then you get first term is 1, and then you get the first order term is trace of Hessian of u, and t plus, you have some t squared, you have some other like coefficients, and at the highest power, you get determinant of Hessian of u. So here, because of this, I mean, this has kind of the full nonlinearity for that you can make out of Hessian, like multiplying all the eigenvalues. Okay, and the Laplace equation is linear. You just add these eigenvalues. So this is called a fully nonlinear equation. So there are much study. I mean, people want to understand fully nonlinear equation. Kind of trying to extend some linear theory to like this type of fully nonlinear equations. Okay, that's one thing. Another thing is the following. So here, Hessian of u is non-negative, right? For u convex. Okay, and then there it's kind of maybe it'd be better not to go into any details. So here, when this Hessian of u is non-positive, this determinant of Hessian of u, this equation it has kind of ellipticity. So it is called fully nonlinear elliptic equation. And the reason why you have ellipticity, maybe I better not to explain now, but you may see later, okay? But such equation is called fully nonlinear elliptic equation. So of course, if you don't have this property, then this equation can be hyperbolic or others. Okay. But because of this non-negativity, when you consider this, it is fully nonlinear elliptic equation.
Thank you.
Other question? But that is great question. So if you open a book on fully nonlinear elliptic PDE, one of the most important example is a Monge amplification. And to tell you maybe some interesting story. Okay, you can consider this kind of Monge amplification in complex analysis too. Okay, I cannot explain it well, but you can consider some kind of determinant of some kind of Hessian in complex analysis, and they are still called Monge amplification there. And you may know that Xingtung Liao got physics medal probably in 80s or 80s or something. He got physics medal by solving a complex Monge amplification. And then that result is called Calabi-Yau theorem. Okay. Oh, okay. So maybe another interesting story is that so Alessio Figari got physics medal in around 2018, and there one of the citations for his work is that he developed some he got some result in some kind of Monge type equations, something similar to this. Okay. Now we have this Monge amplification. Then you may wonder, okay, so what's the point? So what? Well, is it interesting? Or okay, at least to me, it's interesting because it has some nice PDE. So if you like PDE, you may like it. But some of you may not like PDE, possibly. But still, I think you may still like it if you see these nice consequences or applications of having this Monge amplification. Okay, which is of course the result of Brenier solution. So Brenier solution we have. So for optimal transport mapping, we have this Monge amplification. Okay. And then because of this, we can derive some very nice properties of this optimal transport mapping. So somehow this Monge amplification gives us a tool to derive some more information about the transport plan. Okay. So if you understand this Monge amplification better, then you understand more about your optimal transport mapping. Okay. Yeah, that's the spirit. And one of the reasons why the optimal transport mapping, Brenier solution has some nice properties. You already learned this, mechanism displacement interpolation, right? Displacement convexity. This nice property actually came from, it's just property of Brenier solution, okay? And then that can be seen from the Monge amplification. And one of the most important reasons is that this Hessian is non-negative, okay? Because of the convexity, okay? And out of this non-negative Hessian, some very nice thing is this geometric arithmetic inequality. The determinant, the geometric mean, which is of this matrix, the determinant of, yeah, this is nothing but lambda 1 times lambda d to the power 1 over d. So this is the geometric average of these non-negative numbers lambda I. Okay, and that is less than or equal to the arithmetic mean. So this property is somehow very useful. Okay, it gives some extremely nice property for the Brenier mapping. You'll see in a moment. So today we'll do two such applications. One is a very simple proof of isoperimeter inequality. Isoperimeter inequality is something very famous in geometry. It's something very interesting and very old. It's like more than 2,000 years old history, that kind of thing. And then also another very interesting thing is so-called Caffarelli's contraction theorem. So we will consider these two interesting things today, but later you will also learn that using this Monge application with this kind of property for Brenier solution, you can prove some other interesting things, including log Sobolev inequality in like probability. Okay, and it has many other consequences. Okay, so yeah. Okay, any question so far? Okay, let's move on. So one may consider, okay, so where can I start? Okay, let's just start with this. You may consider source and target measures that are just uniform measures. So mu is a uniform measure on some domain X, and nu is a uniform measure on some other domain, let's say Y. Okay, so we assume that they have the same volume because that's kind of the assumption for optimal transport. Okay, and then you can find uh, you can find so this norm of X means the volume. Okay, norm of Y is the volume. So, okay, with the same volume, and then you can find the optimal transport between this source measure and target measure. Okay, and then there for the Monge application, the density G and density F are just one for uniform measures. Mu is just uniform measure, nu is uniform measure, so their densities are one. So this is one, this is one. So what you have is just this equation. Determinant Hessian of U is equal to one. So that is the Monge application for our Brenier solution. Okay. And this mapping T, so given X, you have this Tx, right? So you can view this T is like kind of vector field because at each X you have this, let's say, vector Tx. Okay, so you can view this as a vector field. Okay, then this T, X to Tx is a vector field. This vector field, okay, for example, you can consider the divergence of that vector field. So divergence, you just differentiate each component by the coordinate of the component, right? And then take the sum, which is nothing but the taking the trace of this Jacobian matrix. But T was gradient U, so this Jacobian matrix is nothing but the Hessian of U. So the trace of Hessian of U is the same as the divergence of this vector field. But we know that this is like geometric average, and then this geometric average is less than or equal to this arithmetic average. Arithmetic average is this, okay? So this is less than or equal to 1 over d trace of Hessian of U. So because of this, trace of Hessian U is bigger than or equal to D. D is the dimension. Okay, so that is this thing. So this vector field T has this divergence bound, lower bound, bigger than or equal to D. And this property, UEC, is basically, this is isoperimeter inequality, but of course it's not the isoperimeter inequality we are familiar with. So what is the isoperimeter inequality we are familiar with? It is this. We consider any bounded open set with smooth boundary in this D-dimensional space. And suppose that domain has the same volume with, let's say, the unit ball. Okay. Of course, it can have other volume. We can just normalize this set so that it has the same volume as the unit ball. Then it says the unit ball is the set having the least perimeter, the least surface area. Okay. So surface area of a set having fixed volume is minimized at a ball. So ball has, in other words, ball is the set having the largest volume with a given surface area. Or with given volume, ball has the smallest surface area. Okay, that is what isoperimeter inequality says. Okay, and to have this least volume, the set has to be a ball. Okay? There's no other set than the ball having the least possible surface area given the volume. Okay, that is isoperimetric inequality. And if you know some history, it is more than 2,000 years old question whether this is really true. And then it's like a DDoS problem if you like DDoS, Queen DDoS problem. Before it's, this is something, it's kind of long time ago. Okay, and then can you guess when it was first rigorously proven? This statement. Of course, dimension one is trivial. So let's say starting from dimension two, can you guess when it was first proven, at least in mathematics literature? Actually, less than 200 years ago. It's well after Newton. Newton or Leibniz. I think the first one is Adamad. So they prove it. It was first proven in 2D. I think the first method used Fourier analysis, something like that. Okay. And then for 3D or higher, I don't know, probably around like early 1900 something. Okay. Yeah, so this is still a hot topic of research. There are many variants of this isoperimeter inequality. You can consider not just Euclidean space, some other spaces, and then you may have some corresponding, let's say, statement. And in particular, I mean, to tell you something, some interesting thing, this is like more than 100 years old conjecture called Gartan-Adamad conjecture. Says the same. holds for in X, the X is non-positively space. So if the underlying space has curvature non-positive, then and it is reasonable to kind of consider similar result, expect similar result, but it hasn't been proven yet. If you prove this conjecture, then you will appear in a newspaper, I'm sure, New York Times. And of course, in some other spaces, this does not hold in general. Okay. Okay. Question? Yeah, volume is what volume is, right? You mean here or here? Yeah, you have just RD, you have just a D-dimensional volume. Lebesgue measure. Yeah, Lebesgue measure. And of course, your question should be, then how do you define the surface area? It's the same as how you define the surface area of a surface. Okay. Well, there are some other more general way to define surface area. You can just consider. This is a multivariable calculus question, in fact. Okay, nothing fancy. All right. Okay. Any further question before we actually prove this? So now, using optimal transport, you can prove this in a very simple way. It's surprisingly simple. How? Okay, so you have omega as a set in RD, okay? And then let's say you can find an optimal transform mapping by Brenier solution, transporting this measure, the characteristic function of u of omega to the target measure, characteristic function of B1. Okay, you can find it. There's a Brenier mapping. Okay. Okay, then the next one is, okay, it's technicality, but we can just assume that this mapping is smooth, but you don't have to, but just for simplicity, T is smooth, so that you can just carry out the following calculation without worrying about the solid T's. Okay, then what? Then the perimeter, the surface area of this set is nothing but the integral, the surface integral of this function constant 1. Okay, that's surface area. Okay. But now, for each point x, tx is here. Okay, let's say our center is there. So B1 is a centered ball. So then, I mean, it can be on the boundary of ball, but or inside. So Tx is anywhere, like inside or on the ball, on the boundary of the ball. So Tx has the norm less than or equal to 1, right? For any x in omega. Is this clear? Because B1 has center at the origin, and B1 is by definition, so it's by definition all the x, all this y, whose norm is less than or equal to 1. So Tx is so its norm is less than or equal to 1. Okay, because of that, this n dot tx. So what is n? N is uh, this outer normal vector, okay, of the surface. So in particular, n is a unit vector. So this you have unit vector and a vector whose norm is less than or equal to 1. So this dot product is always less than or equal to 1. Okay? So you have this inequality because this quantity is always less than or equal to 1. So you have this inequality, obviously. Fine. Okay, afterwards, okay, this basically this just tells everything. Then this, once you have this surface integral with respect to this outer normal vector, this is nothing but the flux, the outer flux of the vector field T. Convergence theorem that the outer flux is nothing but the interior integral of the divergence of the vector field. That is this. So this is divergence theorem. This outer flux is equal to this divergence. Okay. And the divergence of T is the same as divergence is trace of gradient of T, but that is trace of Hessian of U because T was gradient U. But Hessian of U is bigger than or equal to T times determinant of Hessian of U. Sorry. The trace of Hessian of U is bigger than or equal to T times determinant Hessian of U or 1 to the power 1 over D. But this was just 1 in our case. So trace of Hessian of U is bigger than or equal to D. So this part is bigger than or equal to D. So the integral is bigger than or equal to D times the volume of omega. Okay. The volume of omega is the same as the volume of B1. That's our assumption. Okay. But what is the D times volume of omega? That is exactly the same as the surface area of the ball of radius 1. So this surface area omega is bigger than or equal to the surface area of the unit ball. Okay, so that is isoperimeter inequality. Okay, so this very simple proof, I don't know. I mean, you may wonder why people couldn't think of it before, but it was found only, I don't know, about 40 years ago or something. Okay, so this proof is the idea of Misha Gromov. So Gromov was probably the first person who used this transport mapping to prove and the properties of the transport mapping to prove isoperimeter inequality. Okay. Question? Yeah, yeah. You need smoothness, but I mean, I think even this part can be done in a more general context. But in fact, you can just approximate everything so that you have smooth mapping. Then afterwards, yeah. But you can do this even at the level of non-smooth mapping using, I think, distribution theory. I mean, you have some PDE theory that can handle some non-smooth functions, but still you can differentiate this in some generalized sense, generalized derivative, and so on. Okay. And it is your exercise that the equality case only holds when the omega is the ball. Okay. That's something you can actually do. So that I leave it as your exercise. So that's isoparametric inequality. And the next fascinating result, I mean, which I really like myself, is Caffarel's contraction. Okay. It is from this paper, like 25 years ago, by Luis Caffarelli. Also, this result, I mean, people are considering extensions of this result recently. Okay, it's still a hot topic in research in optimal transport. Okay, but what is the basic theorem? It says the following: consider on ID Gaussian, and on ID. Okay, Gaussian is like e to the minus q. Okay, q is a quadratic function. Okay, and then you consider uh, uh, so-called log concave perturbation. So with this e to the minus q times e to the minus v, where v is non-negative here. Hessian of q is just identity. Okay, so this is a quadratic function. So e to the negative quadratic function is times constant is Gaussian. But now you perturb it by this e to the minus v, while v is v is convex. So negative v is concave. So if you take the log of this e to the minus v, then you have negative v, which is a concave function. So this is called log concave perturbation. So log concave perturbation in the literature. Okay, because if you take log, then this logarithm of this is concave function. This is a log concave perturbation. So then this log concave perturbation, because you multiply this like exponential of negative v, the decay, the, de the decay of that, the corresponding distribution is faster. In other words, this distribution is more concentrated near the origin. Okay? If this is like this, then if its low concave perturbation is more concentrated in the mean, at near the mean of that distribution. Okay, that's the typical property. And then you may consider some transport mapping from here to there. Okay, and because this is more concentrated, this mapping, because I mean, okay, so this is more dispersed, and then you kind of map it to a more concentrated distribution. So the mapping, at least in average sense, should be contracting, right? You don't want to expand this distribution. If you expand this distribution, you will get some more dispersed distributions, not this kind of more concentrated distribution. So to get this more concentrated distribution, you want to kind of contract such, you want to have some kind of contraction as a mapping to transport this to this more concentrated distribution. So that's the intuition, okay? And Caffarelli proved that, in fact, the optimal transform mapping from here to there is a contraction, not just in average sense, but pointwise sense. Okay, so let me read it more carefully. So Q is a quadratic function. So this is a this e to the minus Q is like Gaussian. Then you have this low concave perturbation. Okay, so here we are assuming that mu and nu have the same total mass. Okay, and then you can consider the optimal transform mapping. The original distance between x and y. Okay. So that is a theorem. Okay, so here, this transport condition is like kind of volume preserving condition. It's like if mu and nu are like a volume of some sets, this is like volume preserving. But of course, this is more general. In our case, mu are this Gaussian measure and nu are this like low concave perturbation of the Gaussian. But this is like similar to the volume preserving property, which was in the previous isoperimeter inequality case, which was like this property, right? And then in the previous case, the map has this kind of volume preserving property, and then it has this additional property for its divergence. Okay. Okay. For its derivative. So the trace-off derivative of the mapping has some property. Then we were able to prove this isoperimeter inequality. Here is similar. You have some kind of volume preserving property for mapping T. And this contraction property, you can translate in this derivative of T. Because if you differentiate this, then from this you get that derivative of T has norm less than or equal to 1, right? So such a mapping T has this kind of volume preserving property and this property for its derivative. Okay. So we had a similar situation in the proof of isoperimeter inequality. Now we have similar or mapping having similar property. So one may expect that having this kind of mapping can be used to prove something nice, some kind of isoperimeter inequality. Okay. I'm not going into details, but we will discuss this aspect more later lecture. That having this transport property and this kind of control of the first derivative of the mapping will have consequences in improving some kind of isoperimetric inequality. Okay. So, for example, log Sobolev inequality is one such an example. Okay, there are but many other types of isoperimetric inequality, and in fact, Caffarelli's theorem gives a very like general isoperimetric type inequality related to the Gaussian measure. Okay, so and then there are many other cases where you want to prove some inequalities related to beyond Gaussian measure, something more general than Gaussian measure, and then toward such direction, proving some kind of isoperimetric inequality uh, related to something more general than Gaussian measure. Okay, people are trying to extend Kappa's contraction theorem for that more general measure than this. Okay, so this is still hot topic of research these days. All right. Okay, so now let's prove Kappa's contraction. But before that, any question about the statement? Okay. So let's start proving it. So we are going to use linear solution for our T. And then linear solution has this Monge application. So we are going to use Monge application. Okay. How? So we find an optimal transform mapping given by gradient phi, okay, which transports that mu to our that nu, okay. And then we want to show that that mapping has this control on the first derivative, okay? But that control of the first derivative of the mapping is the same as controlling the second derivative of this function phi, right? So t is gradient phi, so gradient t is Hessian of phi. So this inequality is of course the same as gradient t is bounded by 1, which we wanted to show. So this is what Kappa's contraction wants. Okay, this is what we want to have. So that is equivalent to proving this, that Hessian of phi for the Brownian solution is always bounded by 1 in this case. Okay, that is what we want to show. This is so this means all eigenvalues are less than or equal to 1 for all eigenvalues, or for each x. Okay. All right. So to prove this, we are going to use this Monge application, and probably that is the only one we can use, right? I mean, for phi, this is basically all the contains this Monge application contains all the information about phi. So we have to utilize this. Okay. Okay, now nu was okay, so mu was e to the minus q, and nu was e to the minus q minus b. Okay, we take logarithm of this equation. Then you have log of determinant Hessian. Then you can, this one is e to the minus this. So you can bring it to the right. Then you have this. So mu was e to the minus q. So this equation is the same as this after taking logarithm. Okay, so this is our equation for phi. So we want to prove that when phi satisfies this equation, we want to prove its largest eigenvalue of the Hessian is always less than or equal to 1. That is what you want to prove. Okay. By the way, I'm following Kapala's proof. Now, so maximum eigenvalue is less than or equal to 1 is, so this is the same as uh, maximum eigenvalue of Hessian of phi is less than or equal to 1. So this is what this statement says. So to get such a result, probably if you learn PDE, then maybe the most people in PDE will try exactly what Caffarelli did. So called using maximum principle. Okay. So the idea is the following. So you just find the maximum point. So suppose you find X. So here, this means you have some directions. So you have two things. The location where you differentiate and the direction where you differentiate. Okay. So here's, so you assume that we are at that location and that direction where this Hessian, oh, so this second derivative is the maximum. Okay. Then using, at that point, using the maximality, and you analyze this equation. What is the idea? So at maximality, what happens is that this is like a maximum. So if you differentiate this once in X, that should be 0, right? It's a maximum. So it's a critical point. And it's maximum. So if you differentiate it twice, then it should be non-positive. So at maximum point, you can apply this, right? So you have, at maximum point, you have 0 derivative, and the second derivative is non-positive. So that's the point. There's features that you can utilize. So at maximum point, you have such property, but then you differentiate this equation and use that inequality to derive some information about the maximum value. Okay, that's what usual maximum principle method would do. All right. So let us carry out that idea. Okay, fine. Okay, so once again, the derivative is a function of two things, location and the direction, like this. And then suppose there's a maximum occurs at a particular location and a particular direction. Okay. So here, existence of such x0 c0 is non-trivial. So somehow, I mean, why? Because in our case, our domain is RD, the whole Euclidean space. Okay, so finding a maximum point in this non-compact space is not automatic in general, right? So somehow to ensure that there is such a maximum point, you have to do some work. Okay, so that is a subtle part in Caffarel's method. I'm not going to do that because it's a subtle part, right? But okay, suppose you can find such a maximum point, and then let me do the rest. Okay. Okay, so this one now has the maximum eigenvalue in the direction c0, but I mean at some direction. But of course, I mean we are in ID, so there's no reason why you cannot take this as your x1 direction, right? You can just choose that coordinate in that way. I mean, choosing coordinate is our freedom. To choose that coordinate in such a way that what happened? Sorry, I don't know what happened. Okay, let's just keep doing this. Sorry about that. Okay. Where are we? Okay, right. So let's just take that direction as our first coordinate. Okay. Just to make our computation just have clean expression. It's not this essential, just it's a naming. Okay. Okay, now you have this equation. Now at that point, x0, you differentiate this equation, these expressions in this direction. This direction E1 is nothing but the direction C0, the direction where the second derivative is maximized at x0. Okay, so you differentiate this twice. If you differentiate first, then this log determinant term, this is your exercise. Okay, this is very annoying. I don't know how to. Okay, let's just keep doing this way. Okay. The log determinant of the matrix A. So let's say matrix A is some differential function of t. And if you differentiate this once, then you get this trace of A inverse and A prime. Okay. This is something you can do. Okay. If you get trouble, just try this. Determinant of A is just this product of eigenvalues, and each eigenvalue is a function of t. Okay, then try this. Then trace A is sum of eigenvalues. Then if you differentiate this, you get something related to this. Then you can rewrite this as this trace of A inverse A prime. Okay, and once you get this expression, you can differentiate it one more time. Then you differentiate this expression one more time, then you get this expression. Okay. Good thing about this expression is this. Here, this is a symmetric matrix. So this part is like B transpose B for some matrix. Okay. And you have trace of B transpose B. Okay. Here B is A inverse A prime. That. Then trace of B transpose B. So this is And P transpose B will give us, let's say if B has some eigenvalues, let's say mu1 through mu n, then B transpose B has eigenvalues what? The squared eigenvalues. So the point is that this trace is always non-negative. So this negative trace is always non-positive. Okay? So that's one thing, and then you have this. Okay, now you differentiate this twice in this first coordinate, which is the same direction as C0. Then on the left-hand side, you get this expression. Okay? And this trace is non-negative, so this negative trace is non-positive. So the left-hand side is less than or equal to this. But then, if you look at this, what happens? Here, this Hessian matrix is non-negative. So its inverse is also non-negative and this one, so this, as a function of x, this one is max at x equal x0, right? That's what our assumption was about this x0. X0 is the maximum point, and this direction 1 is the maximum, the direction which gives the maximum second derivative at x0. So this is maximized at x0. So that means its second derivative is non-positive because it's maximum at x0. So this is non-positive. And this is non-negative. So this whole thing is this whole thing is non-positive. And this whole thing is non-positive. So this whole thing is non-positive. Okay. So the left-hand side, the second derivative of the left-hand side is non-positive. Then what is in the right-hand side? In the right-hand side, you differentiate this. Okay, Q is a quadratic function. So if you, Q is just what? Q is just x squared over 2, right? If you differentiate this twice, you get just -1. That's what this is. And then the other part, now you differentiate this whole thing, okay, twice. So first derivative gives you this derivative of this and the derivative of the inside one. And the second derivative will give you the derivative of this and then derivative of the inside one times this inside one and the derivative of this guy is the right product rule, sorry, the chain rule and product rule. Okay. And then here, this one, Hessian, I mean, second derivative in one of gradient phi is the same as gradient phi of Hessian, the second derivative of phi, right? You can just exchange the order of the derivative. But this quantity is maximized at x0. So its derivative at x0 is just 0 because it's maximum at x0. Okay? So this part is gone at x0. And then this part, the remaining part, this Hessian, Q is the quadratic function. So Hessian of Q is just identity. But V is convex function. So Hessian of that is non-negative. Okay, so let me go on up to 1230. So then this quantity is bigger than the identity. Okay, so this is 0 because this is 0. So this whole thing, the same as, is bigger than or equal to this identity times this one, but this one is nothing but square of d1 gradient phi at x0, right? So this is exactly gradient derivative of t squared at x0, right? Because t was gradient phi. Okay, so what do we have? So on the right, we have this -1 plus this quantity, which is bigger than or equal to this, which is Yeah. This. Okay. Okay, now the left-hand side is less than 0. We already had. And the right-hand side is bigger than this. So if you just consider that, then you get this. Okay. So this implies, so it implies this maximum derivative, second derivative in that direction, the maximum second derivative, right, is less than or equal to 1. That was what we wanted to prove. So done. Okay. Sorry for what